Okay. So good morning, everyone. I would like to start by thanking the organizers for giving me the opportunity to explain some of our recent theoretical work towards studying how would quantum error correction perform in trapped ion devices. So it's a little bit of a mixture of the previous talks by Rainer Blatt and Miguel Ángel Martín Delgado. And what we are trying to do is to try to really make a specific and very detailed theoretical modeling of the ion trap setup, making a realistic modeling for the noise, and trying to see how the errors can be. Let me see. Do I have a light set pointer or? Well, I can continue. Okay, so as we've seen before, one of the main obstacles, as Miguel Ángel was saying, towards practical quantum computation is that systems are noisy and there will be errors. So I will try to keep it as simple as I want. So essentially, any quantum system is surrounded by an environment that creates noise. So for instance, for trapped ion qubits, where we encode information in two particular electronic states of an ion, then there might be, depending on the states, there might be external magnetic field fluctuations that we cannot control. And this will lead to intermediate phases in a coherent superposition that will cause dephasing. So if the time of my experiment is much larger than the T2 time, essentially I will have lose all my coherence of my states and become a classical superposition. And we as theorists, we try to describe these things in terms of quantum channels. So essentially, for this dephasing channel, what will happen is that I describe the evolution of my system is not unitary anymore, but there is a particular phase flip error rate that depends on the time of my experiment divided by this T2 time, and essentially there is this cross map that maps the density matrix of my system towards another perturbed state by the errors that depends on the error rate of the model, and then some Krauss operator that define how this state is being dephased. Okay, so Miguel Ángel was saying that there is different error channels. So in particular, there are ones where you have this phase flip channel that there is only a single Pauli matrix, but then there are other models. And typically in error correction, you talk about bip flip errors, or here you would put a sigma x Pauli operator. And then there are these depolarizing channels where you have the same weight for x, y, and z model, but there are many other physical models of noise that might appear. So not only phase flip, bit flip depolarizing, but there might be amplitude damping. So as Rainer was also plotting in some slides, this excited state has some probability to decay into the ground state. Actually, in an atomic system, there are many levels. So there are not just a two-level system. There are several levels. So it could happen that your state up there might decay to another level, and there might be leakage. So there are many different sources of noise. And what we are trying to do is to come up with a realistic noise model that has several Krauss operators, different rates, and we want to explore the power of quantum error correction in this physical setup. So the idea is that whenever one of these errors occurs, what you do classically is you fight it using redundancy. So you copy your information into several devices, and if an error has happened to one of your bits, then just by comparing, you can recover the original information. Okay? But we know very well that in quantum mechanics, you cannot simply copy quantum information. So the idea is a little bit more involved, and the idea is that you use some sort of redundant encoding. So you sacrifice physical qubits to create logical qubits which are more robust. So this is the simplest case for this 3-qubit repetition code, where you have a logical 0 and 1 that you encode in 3 qubits. And essentially, you can see that you can go from one to the other by applying a global tensor product of Paulis. So the idea is that you fight errors by creating entanglement. Now, a logical state, a superposition, would be some sort of GHZ type state with some entanglement. And the very nice idea of quantum error correction is that you can define some code subspace where you would encode your information. And this is somehow protected, and you can actively do quantum error correction in the sense of detecting whether an error has occurred and correct it just by measuring certain operators, which are called stabilizers. They commute with each other, and essentially you encode information in a subspace, which is the positive plus 1 eigenvalues of this stabilizer, so it will be this ground state over here. Whenever an error occurs, imagine a bit flip error in the first qubit, it brings you to another subspace, and then just by measuring these stabilizer operators, which are products of Pauli matrices, then you discover that this one gives you a -1 sign, whether this one gives you a plus. So this allows you to know exactly that the error has occurred on the qubit 1, so you can actually perform an error correction, and you are not affecting the information that was encoded on the first hand. Okay. So then the idea of making this practical and correcting more than one error is to do concatenation. So essentially you would start encoding one logical qubit into 3, but then you concatenate and you would go increasing the protection of quantum error correction. So to the first level, you can correct a single error. So now your physical error rate now scales with p squared. But if you keep on concatenating to n levels, what you see is that the level of failure, it increases exponentially with the level of concatenation, such that if this 3 over p is smaller than 1, so if the physical error rate is below 1/3, then as you go increasing and increasing your system size, you gain more and more protection. So your qubit becomes exponentially better. Now the problem, as Miguel Angel was saying, is that these error models, they are very limited, and sometimes they're an idealization. So when you do it and you are a little bit more careful and you think that there is not just this environment causing noise, but actually the operations that you do to perform quantum error correction, they can be faulty, then this threshold is not 1/3, but it can become very, very small. So for this concatenated approach to quantum error correction, it can be as low as those numbers. So this threshold tells you that quantum computation is possible in principle, but in practice it will be very, very painful. So now the really jump ahead, or the really breakthrough, is to consider, instead of these concatenated codes, these topological codes for quantum error correction, because essentially the thresholds are much higher, so quantum computation might be possible in principle. Now these topological quantum codes, topological quantum error correction, has several flavors, and what I will be talking about is several distinctions. So no concatenation, we talk about topological quantum error correcting codes. They are non-self-correcting, so what we are aiming to do is some active error correction where you identify the error syndrome and later on correct it. If you want to do a universal set of gates, we will not deal with quasi-particle or anyons, but really you do computations on the ground state or on this code subspace. And we are focusing on color codes because they have several advantages in the sense of the kind of quantum gates that you can do transversally, that meaning doing operations bitwise on all your systems. Okay? So for these color codes, essentially they are stabilizer codes, and you define them on a 3-collaborator lattice where you have qubits residing on the links, on the vertices, and then you define your stabilizers, then defined by the plaquettes. So you define X-type or C-type stabilizers of all the qubits that are sitting on the same plaquette. So they do commute with each other, and you can define a code subspace, and here is where you store your quantum information. Now, if you think about these thresholds, what we are trying to do now in our work is essentially to go more and more physical and trying to see how these codes would develop in an experiment. So if you just consider this environmental noise, such as phase flip or bit flip noise, there are these thresholds which are very high, of around 10%, or they can be even higher if you consider the polarizing noise, as Miguel Angel was saying. What we are trying to do is to really go deeper into the details. So if you don't think about just these errors due to the environment, but really the fact that you are performing some operations that they can be faulty, then you would go and see that the measurement of the stabilizers, they can be faulty, and you see that the error thresholds, they start to go down. And you can be more detailed even, and you can say that, okay, I will measure this stabilizer, which is a many-body operator, and I need a circuit to do that. And each of the elements of the circuits, they will be faulty. And then what you see is that the error threshold, they even go below 1%. So you see that these are numbers of around 10 to the minus 3 or so that would have to be met in the experiments. But they are challenging, it's painful, but it's still much better than the concatenated approach. So if you want to follow some road, this is our belief, is that you should go the topological way. And what we are trying to do is to go one step even further. So if you now want to implement one of these circuits in the trapped ion case, then you can map it to physical operations. And the thing is that you cannot make a model where 2 qubit gates or 1 qubit gates, they have the same error rate or the same error channel. They will require different channels. They do not take the same time, so you need to consider the times of the gates and so on and so forth, and make a model as microscopic as possible, and then try to check if quantum error correction is useful. So we are focusing on the smallest color code, which is the 7 qubit code. We have to measure all these plaquettes in stabilizers in a fault-tolerant manner, and in order to do that, we need to think about how to do it with trapped ions. So there was this experiment by the group of Reiner, where they indeed showed the first experiments towards this 7 qubit color code with the standard or more macroscopic, in a sense, or more standard Paul traps. And what we are trying to do, so for instance, in this figure here, you see how they encoded information in a logical qubit, and they measure the occurrence of one error by measuring these 6 stabilizers of the color code. What we are trying to do is to go one step ahead and seeing how these things would scale towards larger quantum error correcting codes. So we are looking into segmented ion traps, where essentially you have now these microfabricated traps that they form junctions, and you can store ions in different manipulation or storage zones within these arms. And the theoretical idea is that now you start gluing all these junctions into a particular lattice, and within this lattice you will store your ions, where you'll have data ions where you encode your quantum information. They will form the data qubits that encode a larger logical qubit, but then you need ancillary ions and cooling ions as well to perform the stabilizer measurements. So just in a more schematic picture, we are considering that within each of these arms, we have five zones. So we have 2 manipulation zones where you can use Reiner's toolbox with laser-based quantum gates, single qubit gates and entangling gates. But then you also have neighboring storage region where you can store your ions when you are not applying quantum information processing to them. And essentially what you will need is to move ions around so that you can connect part of these ions to an ancillary ion and map the information there. So what is the toolbox? The toolbox that we are considering, it contains all these operations that have been demonstrated one by one in different experiments. So to move ions around, essentially, what we'll need is that at a certain instant of time, we will have a slightly longer crystal, and then we need to split it. This means that we need to play with the electrodes to modify the confining potential, and then split a chain into 2, and then we can shuttle one of these ions to another part of the trap. There is also another application where we will need to bring neighboring ions together and then confine them together in a trap, so to merge a crystal. Then there are rotations, so you can swap the position of different ions. We'll also need sympathetic cooling, so we have another species that we can do laser cooling to cool the quantum data bus, which will be the phonons, without affecting the quantum information that is stored in our data qubits. There is junction crossing, so if you really want to do these topological quantum codes in 2D, you will need to explore the two-dimensional dimension of your codes, so you will need to shuttle ions around junctions and to move them around. And then this is the toolbox that Reiner was mentioning, where you have addressable AC star shifts, global rotations in the equatorial plane of the block sphere, measurement and reset, and also entangling MS gates. So this is what we have to do. This is what we have at our disposal, and now we really want to make not just this, for instance, going from phase flip or bit flip error channels to a depolarizing channel, but really to make a microscopic error model. And what you find here is a table of what is our toolbox. For each of these toolboxes, we have the time of the operation that takes in an actual experiment, and the one that we expect it to take in a few years, say 2 to 3 years with current developments. So here you have a particular fidelity, and this fidelity, it fits into the error rates of the particular error channels that we are using. And as you see here, all these different operators, they are described by a physically motivated error model that contains many different channels. So for instance, for 2 qubit gates, it's a sort of depolarizing channel, but now errors, since you are applying a multi-qubit gate, they do not happen to a single ion, but it happens to 2 ions or 5 ions, depending on what is the the MS gate acting on. And actually they are biased. They are not really X or Z, but they are in all the different axes. But then you have time correlations in the single qubit gates as well. You can have a bit flip channel for measurement and qubit reset. You have essentially for all this crystal reorganization, you have a differential channel, but the rate, it depends on the time of the operation that it takes, okay? And you can see that the model is quite detailed. So now you want to do a particular quantum error correction, and you see these are how you would store your ions, and these are the operations that you have to do. So within each of these operations where you have to map a stabilizer, you compile it into a sequence of single qubit rotation and MS gates. And more importantly now, you see that you have to translate this circuit into the operations that you actually need to do in the IO trap. So you'll have to shuttle, merge, do the mapping, then split, then measure, whatever. And then each of them has a particular error channel. So you translate it into this particular error channel with different rates, and you would like to do a simulation. So as you can see, this is very painful. The complexity grows, even if you are just looking into simplest code and simplest fault-tolerant schemes, or the simplest quantum logic gates. And now the idea is that since you have a multi-parameter error model, you'd like to test whether this quantum error correction can be useful or not. There will not be a very simplistic threshold where you have in the x-axis a physical error rate. So what we are trying to do is to come up with an experiment where essentially you encode a qubit, the task is to decode it, and then you will see if at intermediate times you do error correction, whether it will be beneficial or not, okay? So this is the result for as a function of the time, whether this error correction is beneficial or not, and here is the probability of guessing the state correctly. And what we see is that for current technology, so what we are comparing, what we are asking is actually not to be on the threshold, but something that is even more fundamental. So is quantum error correction beneficial or not? So if you encode the qubits, this is the probability of guessing, it goes down because there is a lot of noise in your problem. Now if you do quantum error correction, what happens is that you start with a lower probability because your operations are noisy, so you're introducing noise into the system. But then the dream is that now since you are protecting and doing active quantum error correction, somehow the slope of this probability will be higher, and at some point you will be better than the encoding without error correction, okay? So this is the regime, which is the least demand to your experiment, where in the sense that doing quantum error correction is better than not correcting. But as you can see, there is still a gap with respect to just the physical qubit. So if you are in this regime, it's better not to encode. So your gates are still not good enough, so you perform this task better without encoding. But now this is for current numbers, and now with the planned future numbers, what happens is that actually you always beat the encoding without error correction, but there is a regime where you perform quantum error correction in a fault-tolerant way with the smallest color code, where you can actually beat, so as you see here, you can actually beat the physical qubit rate. So both encoding and correction is good. So this is just to say that quantum error correction is practical in the future, even with these small, noisy baby quantum computers. And you have to go the painful way, but there is a very good perspective for trap-time quantum computers. And I would like to finish by acknowledging all the collaboration within this equal consortium, this approach where we are trying to model and try to keep a qubit alive. So there are experimental nodes, and in particular, I would like to acknowledge the collaboration with Marcus Muller in the University of Swansea, and together with Mauricio Gutierrez, that are really the leaders and the pushers of this theoretical activity towards quantum error correction in ion traps. Thank you very much.
So, questions? Martin.
I have some, well, probably very simple questions. So one is, in your error models, it sounded always like you put them as, typical quantum channels or random errors. What about, let's say, systematic over-rotations or unitary error? How important is that, or how bad is that for the code? And the second question is, you will also have to do some post-processing. So is this actually, in these settings, is this negligible, or does this become at some point also a limiting factor that you have to take a measurement, you have to compute what you have to do afterwards, and then sort of send around commands through the experimental system?
Yes. So the first question, so at the first stage, what we were trying to do is to somehow, based on microscopic model of, say, MS gates or something like that, then we come up with a quantum channel, and essentially just so doing some analytical calculation fixes the rates. But as you're saying, there's more to a Markovian channel. So what we are now trying to do is, for instance, for MS gates or for single qubit gates, we're really trying to take like the stochastic model of the noise, say intensity fluctuations, phase fluctuations, and so on, or even so intensity fluctuations would lead to over rotations, so coherent errors in a sense. So we are trying to model those, and really, since we are doing for these small codes, you can do full state numerical simulations. You don't need to take the Markovian models into account, but you can do the real unitary evolution, and then we are considering those. And what comes out from the new numerical simulations is that there is still a regime. So it typically, what happens is the more sophisticated your error model becomes, the more tougher it is, but there is still a regime where there can be beneficial quantum error correction, and it's not so much different from the one that we were discussing with these models. And now, so as to the classical compiling, this would be something that has to be taken into account for larger codes, but we are still super far away from those situations. So we are just considering codes where you can indeed, they are so small that you can indeed have a lookup table that will, so you can make decisions on what to correct or not very fast, and this is not a problem. But it will be in a future, whenever you scale it to larger codes, then you'll have to have a proper decoder, and then the classical simulation will play a role, yes. I think that this depends on the code, and it depends on the kind of decoder that you're using. I'm not an expert on that, but for instance, for the key type code that has been studied quite a lot, there are very fast and good decoders. For the color code, they are developing those, and it's a more challenging theoretical problem. I wouldn't know what to tell you. I mean, I think that, so for instance, there are like decoders that are based on matrix product states and so on. So in that sense, I think that things will scale polynomially, but it's also a matter of how do you want to decode and make your guess of what was the error happening. So.
Okay, thanks. Let us then go ahead to the next talk. Thanks again, Alejandro.